Our next topic is two-way tables. This is going to be both an application of some of the material that we've done already to the case of two-way tables and, of course, some new material. So I want to first think about some simple example, like I have two variables, heads and tails, say a coin and a ball or something like that. They can be white or black, heads or tails, just two categorical variables. And for a multinomial distribution where we sort of forget about the two-way structure, we just essentially think of it as a one-way table, we have four probabilities. And these probabilities can be arbitrary as long as they sum to 1, right? That's our only restriction in the multinomial model, or the saturated. So saturated just means it fills out the probability simplex. It's the probability simplex that's being saturated. So there's no restrictions other than it sums to 1. And we thought about having alternative, more restrictive hypotheses. And one thing that this more restrictive hypothesis, the null hypothesis, could be is that it's a single point. That is, hey, there's some PWH star, PWT star, PBH star, and PBT star, some special values. And we'd like to compare whether the, say, empirical values that we get when we do this experiment are equal to this or significantly different from that, right? That was the kind of single point null hypothesis that we looked at for the multinomial case. And we can know that we could compare, do a goodness of fit test. With a Pearson statistic or a deviant statistic. Okay, but that's sort of not sufficient for a two-way table, of course. So why is it not good for a two-way table? Well, it doesn't in any way take into account the two-wayness of this table, right? It's just treating this as a single vector of probabilities. And so we want to use a model. So I like to draw this picture of models. So here's the data point in probability space, and here's the model, which is our null hypothesis. And we think about the most likely explanation. And we have measures of like g squared and the Pearson statistic that tell us, in some sense, the distance, or because these take into account the sample size, they tell us whether or not we believe this point to lie on this model or not, right? And what we'll see a little bit later today is another way of thinking about this distance, which is that, well, what if we actually care about the direction, and we care about whether it's above or below, and we care about how big it is in the sense of how large is the effect or the association. And the other thing that you should think about in this picture is that whereas this model is a single point model, we would like to think about a class of models that somehow reflect the two-way nature of this table, or for a more complicated table, the n-way, three-way nature of the table, right? So there's fancy ways to say that. The way a mathematician might think about it is to say that this table, or matrix of numbers, comes equipped with actions, group actions. Like there's a way to mix up heads and tails, and there's a way to mix up white and black, say using multiplying by a matrix, or just swapping them. And those actions, this sort of general linear group action on both sides of the table, don't mix with each other. And that's one way of thinking about the nature of this separation. Another sort of formal way to think about it is to say that there's some space of outcomes. Here there's 4 outcomes, and it decomposes into a vector space of all possible combinations of heads and tails, the possible probability vectors. you can think about that vector space as coin combined with a sort of an outer product with another vector space for color. Okay. So those are sort of, it's a formal way to think about it. Don't worry about that if you don't like that notation. But, if you're interested in kind of some of the mathematical structure, that might be helpful to think about. But the best way to think about this, what's going on here, is maybe to look at an example of such a model that reflects the two-way structure of the table. And it's kind of our canonical model. It's the simplest type of thing we can look at. And that is that the variables are independent. All right, so that's the model that I have maybe a biased coin, and I have another biased coin. One has heads, tails, one is painted white and black. And I flip them, and they have nothing to do with each other whatsoever. Right? That's a hypothesis about the data. It has two parameters. So it's going to look like this, a surface. And it sits inside of the probability simplex with 4 outcomes, which is a 3-dimensional thing. So we could think about, there's a parameter vector. There's only 2 parameters here. Maybe call them theta heads and theta white. And these are stupid parameters. So probability of heads is just equal to theta heads. And probability of tails is equal to theta 1 minus theta heads. Probability of white is theta w. Probability of black is 1 minus theta w. Okay, so really this is just the probability of heads and the probability of white. But I'm giving it, in general, this function won't always be so simple, this function. And then what we're saying is that the joint distribution of these 2 random variables is not an arbitrary table, but a specific table, a table that satisfies certain conditions, or which can be expressed in terms of these 2 parameters. So our hypothesis is that it's something like the probability of getting white and heads is equal to probability of white times the probability of heads. And this is equal to the probability black, probability heads, probability white, probability tails, probability black, probability tails. Right? So that's a specific hypothesis about the data. It has fewer parameters. So we have this picture. We have some ambient probability simplex, and inside of it sits the models, the sets of probability distributions which come from a table like this. Another way of saying that is that we have probability of outcome ij is equal to probability of outcome I times probability of outcome j. It's called statistical independence. Is there anything else you can notice about this table? So, for example, if a probability distribution comes from this table, so if PWH is equal to PWPH and so on, then there's an equation actually that holds among these probabilities. I know at least one person knows what that equation is. And the idea what that equation is a very small equation. It's quadratic. We're saying in this table that we take a vector PW, PH, PT, and we take the outer product of it with another vector, PW, PB. What can I say about the resulting matrix?
You look at as a matrix, you take the determinant is equal to 0.
Yeah, the determinant is equal to 0. So in other words, PWH, PBT equals PBH, PWT. Right? Or if I subtract one from the other, I get 0. And that's just because, well, if I substitute here, I get PW, PH. And I substitute here, I get PB, PT. I substitute here, I get PB, PH. And here, PW, PT. And those 2 things are just identically equal, those 2 products. Right? So they're equal in a difference. And it turns out, statistically, taking differences like that isn't always so well behaved. So very often we do another thing which is equivalent to that, which is that we say that, well, one of the things that's happening in this table is that PWH, PBT divided by PBH, PWT equals 1. Right? That says exactly the same thing as this. Just dividing by, it's provided that neither of these is 0, just divide by that. So this is a sort of thing that's a little bit better behaved in the statistical setting. So we'll see more of things. Okay, so there's a notion of, what do we learn? There's a notion of a submodel of the multinomial model that reflects independence of these two random variables. It says their joint distribution of these two random variables is independent. And we have various ways to characterize being on that model. And those different ways of characterizing it sort of lead to different measures of goodness of fit, and they'll also sort of lead to different measures of how much do we fail, right? So we could say, well, what is this number? If I take the difference of these two things, that's a measure of sort of how strongly we've separated, or what is how much is this ratio different from 1? Right? So those measure how not independent we are. And of course, because they're expressed in terms of the p's, they don't depend on the sample size. Right? So that difference and that ratio don't have anything to do with the sample size. The sample size tells us whether we think that difference is significantly different from 1 or significantly different from 0. So I may give you an exercise where you draw the picture of what this thing looks like inside of the probability symbol. I won't give it away yet. Okay, so let's turn to an example from the notes to see why this type of situation is such a common thing in the kind of analysis that you'll want to do. So the example from the notes is the effect of vitamin C. This is the online notes. This is an experiment by Linus Pauling. And it's a double-blind study. There are 280 French skiers. And one of them, I don't know, maybe due to a tree or something, had to be dropped out. So it's actually 279. Okay? So we have a table of outcomes. There's placebo, vitamin C, and total. And they had a cold, they did not get a cold, and total. So let's say there was 31 that had a placebo and got a cold. There were 109 that had a placebo and did not get a cold. There were 17 that took vitamin C and had a cold, got a cold, and 122 that did not. And if we just total these up, we get 48, 231, 279, 139, and 140. So these are a table of counts, outcomes. So you could think about the entries in this matrix as random variables. We might write them as like capital Nij. We might write the actual outcomes as lowercase nij. Right? This is just a notation for the counts. In other words, this is n, maybe 1, 1 is 31, and 1, 2 is 109, and 2, 1 is 17, and 2, 2 is 122. It's just, and then the totals, we write a little plus. So we're summing over the second coordinate. So this is n1 plus. This is n2 plus. This total of 48 is n plus 1. And the 231 is n plus 2. And the 279 is n plus plus. So that's the sample size. Okay. Just notation. Okay, so we can also compute from that table the sample proportions. So that's the sample that counts. This is the sample proportions. So there's cold, no cold, total. Of course, the totals will all be something boring. Well, the grand total will be something boring because this is proportions. Placebo, vitamin C, and total. And so this is just, okay, we forget about how many there were. And we sort of have a p++. The sum of all the probabilities had better be 1. And we have a p11, which is 0.111. We have a p12, which is 0.391, and a total for this column, which is 0.502, p1 plus. And here we have 0.61, 0.437, 0.498. And here we have 0.172 and 0.828. I haven't written all the p's, but you get which ones they are. Oh, that's p21, p22, and then there's some versions. Okay. So what kind of questions do we want to ask of this table? Well, if we're comparing it to the independence model, we'd like to know, okay, is it on the independence model? So is it statistically significantly different from the surface of the independence model, right? Which is a lower dimensional thing. We'd like to know, okay, given that information, can I tell you what the direction of association is, right? Is vitamin C sort of associated with fewer colds or more colds, right? That would be kind of the question of, am I above or below this surface? Which side of the surface am I on? I could also ask about conditionals. So that was kind of expressing it as a joint. So, you know, if I think about probability of getting a cold, given that I had vitamin C, versus the probability of getting a cold, given that I had the placebo. So these kind of get rid of, they take the marginal totals to be equal in some sense. And in fact, these marginal totals are pretty much equal. Okay, so this is related to the way that the experiment was designed. We're more interested in these conditionals than we are in the overall joint. Right? The overall joint is not particularly meaningful because there's a treatment condition. This wasn't a random. The ratio between these is not a random. Right? And of course, ultimately, we're interested in causality. Okay, so there's sort of two kinds of association. Are they independent or not? And then this kind of, I only care about the conditionals, not about the joint. And I'll be a little bit more specific about what we mean by those two different types of questions. So I should say, okay, this, of course, is equal to probability of cold and, by Bayes' rule, vitamin C divided by probability of vitamin C. And these things are just numbers from this table. So cold and vitamin C is P21. And probability of vitamin C alone is this marginal total, P2 plus. So that's P21 over P2 plus, for example. And this is another similar ratio. Think about what that is. Okay, so I'm focusing today on this very simple table so that we can really dig into it. But of course, there's many other more complex two-way tables that we can consider, which we will consider. For example, there could be more than two rows. There could be more than two columns. And we learned about different types of variables. So these are binary variables, so I could think of them as nominal or maybe ordinal, though there's no difference. But I could have, an arbitrary ordinal variable, say, where there's an example of your notes where with coronary heart disease or smoking, one parent smoked, mom, dad, or no parent smoked, one parent smoked, both parents smoked, for example. So you can have other types of tables, and we'll have slightly different tests for some of those. But we can always sort of reduce it to And we can always simplify it to a nominal case, and the easiest case, of course, is just these 2 by 2 tables, which is what we want to focus on today until we understand the concepts. Okay, so let me say a little bit more about the notion of marginal and conditionals. So a marginal distribution, well, actually above that is even, there's a joint. The joint distribution, marginal distribution, and conditional distribution. So the joint distribution is this total distribution over all of the possible outcomes together. And it's joint in the sense that it involves more than one variable. So the joint is over some number of variables. The marginal distributions are those where I've summed out one of the variables but not the others, right? So when it's a multi-way table, or I have more things, that becomes, there's more than one marginals, right? So there's marginals, any choice of which variables to sum out. I could sum out all but one, or I could sum out some. In this case, there's only one choice to make, right? So, okay, so the marginal distributions are these things like P1 plus, P2 plus. That's one marginal distribution. The other is P plus 1, P plus 2. The joint is P11, P12, P21, P22. And then the conditionals are these things where I correct for the rows, right? So P21 divided by P2 plus, and so on. P2, P1, and it's, well, what's P? It's P vitamin C. P cold given vitamin C. That's where I divide by these marginal totals. And what distribution it's most appropriate to make inferences with depends on what you care about, and also about how you design the experiment. And we'll see in a second that those are, that in a sense, those are related to the sampling scheme. And one other thing that I would say is that if you have, as long as you have no zeros, once you know the marginal, once you know the joint distribution, you can compute everything. But if you only know the marginals or you only know the conditionals, you don't have enough information to compute everything. So these are sort of less information, or you don't care about some aspect of the problem. Okay, so let's talk a little bit about sampling from these sorts of tables. Implicitly, what we've been talking about so far is multinomial sampling. Remember, that's, in this setting, we're saying that the grand total is fixed, and we have some probability that it shows up in each of the cells, and we're sampling from that. Multinomial, n++, and then whatever our vector. Okay, so now I'm saying in this that where I is the number of rows and j is the number of columns. Forgetting for a moment that we're for general table, not just 2 by 2. Okay, so that's the multinomial, which we're familiar with. The only new wrinkle is that we've separated that vector, we've sort of decomposed it into a matrix with rows and columns. So what are our other points of view on sampling? What kinds of sampling could we have? We have to change the experiment a little bit, maybe. What other types of sampling have we talked about for this kind of data? Poisson, right? So, okay, so what is the story here for Poisson? So we have multinomial, we have Poisson, and we'll see also that there's another type of sampling called product multinomial. Well, two more types, and another type called hypergeometric. Okay, so we already saw hypergeometric, and we'll adapt Poisson, and product multinomial we'll come back to. So it turns out that product multinomial is probably the most appropriate for the situation. It's the one in which these rows are fixed. Right, so you can see in this experiment, it's very unlikely that you got 139 of these and 140 of those by chance. Right? So this is part of the experimental design. So that's neither. So multinomial said n is fixed, everything else is random. Poisson says nothing is fixed, everything's coming at a rate. Hypergeometric says all the totals are fixed. We'll see that at the end. And in between, there's something called product multinomial that says the rows are fixed, but the columns are not fixed, or vice versa. And that's often the case for experimental design. Okay, so let's look at Poisson. Okay, so the picture is we have some table like this, cold, no cold, placebo, vitamin, and instead of there being true probabilities, what there are true rates. Lambda PC, lambda PNC, lambda VC, and lambda VNC. And the scenario, which is not the scenario for this experiment, but the scenario you should think about is, someone's sitting in the lodge, and every time somebody comes in, they ask them, hey, do you have a cold? Have you had an orange today? So in this one, of course, this n++ is not fixed. And each cell is Poisson with rate lambda ij. And these are all independent. And we know their expectations and their variance. And we want to ask a question. Our questions are something like, are the rates in the cells the same, or are they different for different cells? And so there's, it feels a little arbitrary deciding whether or not what kind of experiment this was, in a sense. And there's I think this is just going to hang in my, it goes up higher. There's a sense in which you could formalize the relationship between the multinomial and this Poisson through this quantity. Another way to say that is that you can factor the probability distribution into, for a Poisson, multivariate Poisson, into one Poisson for the total, and multinomial Nij multinomial for this n, which is fixed by that, and then the relative parameter. So if we're doing the sit in the lodge sampling scheme, even though the truth is that it was a Poisson sampling, if we don't really care about doing any sort of inference about the total rate of skiers coming down that day, which in this example we don't care about, right? If I'm the owner of the ski resort, I definitely care about that. But if I'm just trying to find out if vitamin C is good for you, then I don't care about that. And so I can factor out that total and break the the Poisson distribution into just something for the total and then a multinomial for each n. And so I can do my multinomial style inference and get valid answers. Yeah. So in other words, the inferences about this quantity, which is pi ij, or pij, our inferences about that quantity will be the same. Right? They're not affected by this change. Okay, so and you can see, it's sort of easy to imagine how that works. But of course, there's a proof that shows that it factors in that way. And that's a general strategy that's useful for lots of situations where you take a probability distribution that you're interested in and you factor it into simpler distributions and analyze it that way. So I think it's easy to believe that it's true, but it would be a fact that requires proof, which I'm not going to give you. Okay, so that's Poisson. For the multinomial, we've already discussed, and we know what the expectations are, just n plus plus times each of the proportions. And we know how to compute the variances. So then, of course, neither of these sampling schemes, Poisson and multinomial, are what Pauling actually did, right? Because we don't for a second believe that this 139 and 140 were achieved randomly. So he very carefully selected his two groups, or randomly distributed who had placebo, who had vitamin C, so that these numbers would be, well, intended to be equal, except that one person had to drop out, right? And conceptually, of course, this is related to the idea of conditionals, right? So if I'm fixing these numbers, then the relative value of these numbers don't matter at all. What matters is the ratio of P21 to P2 plus, P22 to P2 plus, and so on, or the ratio of 31 divided by 140, 109 divided by 140 versus 17 divided by 139, 122 divided by 139. So what matters in this case of what actually happened, or what's called the product multinomial, our focus is on the conditionals. And we're thinking of whether we had vitamin C or not as a treatment. And we're interested in, and we're fixing the number in each category. So instead of thinking of n plus plus is fixed, though it is fixed, we also fix in this case, the row totals. N1 plus and N2 plus as fixed. So what happens if we do that? Well, then inside each row, we just have multinomial sampling, right? Totally straightforward, one-dimensional multinomial sampling, one-way multinomial sampling. So inside each row, we have multinomial sampling, and these rows, because we fixed this outside total, are independent. Not identical, of course, but independent. And then we can compute the likelihood, or the probability distribution function, by taking a product of the likelihood for each row. That's why it's a product multinomial. So taking a product of multinomial likelihood functions. So let me write that out. So, okay, so suppose I have an I by j table. So I and j are positive integers. And I have samples of size n I plus, I equals 1 up to big I, j equals 1 up to big J, but we're summing over that one from I groups. So in this case, I is 2, and the groups are C, vitamin C placebo. Right? So the marginal counts are fixed. So we have for each row a J category multinomial. We have a multinomial for each row. And we have I groups of them. And each row has its own parameter. Parameter vector, J minus 1 free parameters. Here, J minus 1 is equal to 1. There's only one free parameter in each row, but each row is separate. And we want the probabilities, J given I, as I sum over each row to equal 1. This means to be a conditional probability, right? When you sum over them all, you get this number. Okay, so the joint of n, the random variables ni1 up to nij, conditioned on the row totals. So we're fixing the row totals, right? If we don't fix the row totals, if we just fix the grand total, it's going to be multinomial. If we don't fix anything, it's going to be Poisson. But we're saying we're fixing the row totals, and we're computing the joint of the random variables, which are the counts in each of each one. Oops, I should have an I here. Oh, there's an I here. Okay. Has probability distribution. Probability that ni1 equals nI1, nij equals little nij, big J, given that ni plus, the row total, is whatever it is, and so on, right? Given that all the row totals are fixed, is equal to ni plus factorial divided by the product j equals 1 to j, nij factorial, product j equals 1 to j pi, j given I apologize, I'm switching back and forth between pi and p, but you could think of this as, let's make it p, j given I to the power nij. Okay, so for each little I, I get that distribution. And then assuming that the samples are taken independently, I can combine that into a likelihood function. Not the log likelihood, but the likelihood. So the likelihood function is the product I equals 1 to I. So this is the product over multinomials that is advertised by the name. Ni plus factorial divided by the product j equals 1 to j, nij factorial times the product j equals 1 to j p j given I raised to the power nij. Okay. That is our likelihood function. And again, this is appropriate when, and you'll find, as we get through this week's homework and exercises that you're not going to need to do this by hand, but this is the procedures are baked into R or whatever you're using, and so we'll spit out the answer, but I want you to understand where it's coming from. So it's appropriate when the row totals are fixed, like we have a treatment. We have stratified sampling, sampling or treatment group, clinical trial or something. Stratified sampling is where we kind of simulate a clinical trial by choosing people from the population in some way as to fix those totals. Okay, so can you think of another situation in which it's appropriate, even when the totals are not fixed by the design? When what? So we think, would it be appropriate, for example, in the sit in the lodge version of the Poisson, of the Pauling experiment, the Poisson sit in the lodge version, could we use this kind of sampling hypothesis or product multinomial likelihood for any questions about that situation? Even though that's not really how the data was generated. The answer is yes. It has to do with what I just erased, which is that you should think about the product multinomial sampling scheme as intimately connected to the idea of conditionals. So if all I care about is the conditionals, I fix the row totals, or I don't care about the row totals, and I only attempt to do inference about the conditionals, then it's okay to think about the data as coming from such a sampling scheme. So we only care about the conditionals. And just as with the fact that I can turn a Poisson into a multinomial by factoring out the Poisson distribution for the total number in the sample, the total number of skiers coming down the hill, I can justify this statement by factoring the distribution into, or the likelihood into a multinomial for the row totals n 1 plus, n 2 plus, and I plus with big N, N, and the vector of parameters Pi plus, P1 plus, P big I plus. Right? So otherwise I take this table and I just say I can think about this as being a multinomial. So I collapse this part and say, well, this is a multinomial distribution. This is the n, and these are the counts, right? So I factor it out into a multinomial for the row totals, and then independent multinomials in each row. Ni1, Nij, with parameter vector Pj given I, and total, the subtotal for that row, n I plus, that came from this part. Okay, so that tells us that for these tables, these two-way tables, I have lots of different choices in how I interpret the data. It seems kind of unfair because the sampling scheme doesn't have to match the sampling scheme that I actually used or that I believed was the generating process. And it's not that it doesn't matter, it's that it doesn't matter. It's not true. What's true is that it depends, that is the sampling scheme you're allowed to, let's say the sampling or the likelihood you're allowed to use depends on the questions that you're asking. If I don't care about doing inference on the grand total, then I can treat that as a Poisson and the rest as a multinomial. If I don't care about the row totals, I can treat that as a multinomial and the rest as So whatever the questions that I'm asking of the data, if I care about the conditionals, about which parameters I would like to compare, that determines which sampling schemes are sensible to use. Okay. So there's one more way that we could think about this same table, which was way number 4. And that's that we can think about it in terms of hypergeometric sampling. So in hypergeometric sampling, this was the example where I have an urn. It has a bunch of white and black balls in it, some fixed number. I draw them out. I draw k balls out without replacement, and I see how many I got of each color. Right? How does that fit into this? Well, it happens when both the row and the column totals are fixed. And it's a more restrictive situation. And we'll see later. So this leads to these exact tests. And we'll see Fisher's exact test later with this example of lady testing T. But let's just map how exactly this relates to the urn model. So let's have a table. Draw. I drew the ball. I didn't draw the ball. Right? Those are the two outcomes from the point of view of the ball. Either it was drawn or it was not drawn. And then it has colors, let's say red and blue. So I have a red and blue ball. I either drew it or didn't draw it. And that's sort of all the ball can tell about the world. And I want to draw little n balls without replacement. There's a total of n balls. In the urn. There are big D less than or equal to big N red balls. And K is my random variable. So or K is the number of, I'm interested in the probability I get K red balls out of the N that I draw. So those are the variables, but those are the numbers that show up in the problem. Right, so this would be like draw, didn't draw, red, blue. If the row and column totals were fixed. And then I get probability of K, N, D, N. Is this hypergeometric distribution D, K, N minus D, choose N minus K, divided by N, choose N. Okay. Okay. And as someone observed on the Piazza forum, that in some cases, some software will default to an exact test if it can figure out that, which essentially uses this kind of logic, if it can figure out that the asymptotic tests will perform poorly because there's small sample size or whatever else. So sometimes your software will automatically switch to an exact test, and we'll talk later about how that works precisely. Okay. So let's see, either I can walk through the worksheets on overdispersion or continue with tests of independence. Which would you like? Independence. Okay. Okay. So again, we want to separate our thinking now with this picture into two components. One, given the data, is the data I observed significantly far away or significantly, can I reject the hypothesis that it's on the independence model? And secondly, what direction is it and how strong is the effect? So the test for independence is going to focus on the first thing, and then we'll talk about the second thing, which is the strength of the effect and the direction. Okay, so we learned about two generic tests for goodness of fit, and that's what we want to use here. That is the Pearson and the deviance. So we know already some facts about what the independence model looks like. If we know the marginals, once we know the marginal distributions, we just multiply them to get the joint distribution. And we know that the determinant is 0 and that this other ratio that we wrote on the board is equal to 1. And so our hypothesis test that we want to do is going to be sort of a scaled version of that, which is that, okay, the independence model is true. That means that we believe that the cell probabilities are just equal to the product of the marginal probabilities. For all pairs ij. And the alternative hypothesis is that that's not true, but with saturated model is needed to model the data. That is, this relationship fails to hold for some pair. And it's enough for one pair to fail for the whole thing to fail. So this is the determinant is 0, or if it's a bigger matrix, all the 2 by 2 determinants you could construct are 0. And but that's not true. And so we just proceed by the usual approach for a goodness of fit test. That is, first we get the expected counts. Here, whereas for the generic multinomial case, we only had one index. Now we have two indices. Counts under the null. Then we compare using our test to the observed counts. And then we calculate our test statistic to decide appropriate degrees of freedom. What are the degrees of freedom in general? Well, here's an easier question. What are the expected cell frequencies? I have a 2 by 2 table. Everything adds up to n plus plus. This is n1 plus, n2 plus, n plus 1, n plus 2. What are my expected counts? These guys. Or my expected probability. Or what's my maximum likelihood estimator for the independence model? So if the independence model is true, okay, so how about this? What's the marginal proportion? So what is this marginal proportion? Like I just erased it in that other table. N1 plus over n plus plus. So this one is n2 plus over n plus plus. Okay. And over here I should n plus 1 over n plus plus, n plus 2 over n plus plus. Okay. So what's the proportion that I put in here? That's called p hat 1, 1. Or sample proportion under the independence model. Yep, so it's just a product of this proportion and this proportion, right? That's what our hypothesis is that if it's independent, this probability should be this probability times that probability. Right? So this is n1 plus n plus 1 over n plus plus, n plus plus. So then what's the expected count? E11. This is a multinomial model. Yeah, so it's just this number times the total. N plus plus P11 hat. So I could one of these n plus plus cancels, although I find that sort of confusing because it sort of gets rid of this relationship, but you could also write it this way. Okay, so that's the expected count. Similarly, if I change 1 to 2, either of these 1s to 2. So now I know how to fill in all these expected counts. The observed counts are just whatever the observed counts were, and then I have enough information to compute my Pearson or my deviance, right? Let's write that down. Okay, so Pearson is going to be sum from I equals 1, and I'll have an I by j table. Sum from j equals 1 to j, nij minus n pi ij over n plus plus pi ij. So this is just this calculation. And in terms of observed and expected, I equals 1 over 1 to I, sum from j equals 1 to j. Observed, ij minus expected, ij divided by expected ij. And I want to square that. Okay. Oh, I have to square that. Because it's the same as the formula for the one-way table. It's just that we have two indices that we're keeping track of for each of these. So it's exactly the same as the formula for the one-way table, except for how we calculate the expected values. So it's the usual multinomial g squared with just a particular scheme for calculating the expected values, which is baked into this notation, so that we can remember that's how we calculated it. And then it depends on two variables instead of one variable, conceptually. And then the deviance, it's Pearson. Deviance. G squared is 2 sum I equals 1 to I, sum j equals 1 to j, and ij log n ij divided by n pi ij. And this is log base e, by the way. And I can do it in terms of observed and expected as twice sum from I equals 1 to big I, sum from j equals 1 to big J, observed ij log observed ij divided by expected ij. That's the likelihood ratio version. Both of these things are asymptotically chi-squared with these are chi-squared with some degrees of freedom. Which degrees of freedom is it? Well, suppose I have an I by j table. How many free parameters does the I by j table have under the unrestricted multinomial, the saturated model? How many free parameters does the 2 by 2 table have? Sorry? How many free parameters does a 1 by 1 table have? A 1 by 1 table of probability has 0, right? Because it has to be 1. So that tells you the answer, right? Must be the number of cells minus 1. Okay? How about the independence model? This is also equal to the dimension of the probability simplex, right? Space of all possible probability distributions. The independence model has how many free parameters? Well, there's no 1 by 1 independence model, so that won't help us. We'll have to go to 2 by 2. How many does the 2 by 2 table have? I have P1, P2, Pi minus Pi, which is equal to P1 minus P1 minus P2 minus Pi minus 1. Right? And we have P1, P2, up to Pj, and Pj is equal to 1 minus these. Right? And then the cell inside is just Pi, Pj. Right? So how many free parameters does it have? Well, what's an upper bound on the number of free parameters it has? How many numbers do I need to tell you that whole table? Yeah, I heard something that was close. Well, that would be too many. Because I times j, we only lose one parameter, but it's much more restricted than that. So it's just, well, I get I minus 1 parameters here, I get j minus 1 parameters here. Once I know those, I know everything. So this has I minus 1 plus j minus 1 parameters. So what's the degree of freedom for the chi-squared? Yeah, it's so the degrees of freedom, which is sometimes written nu, is the number of free parameters minus the number of model parameters, number of for the saturated, number of free parameters for the saturated minus the number of free parameters for the model, the degrees of freedom for the saturated minus the degrees of freedom for the model. So that's ij minus 1 minus I minus 1 plus j minus 1. So it's the codimension. It's the dimension of the simplex, or the dimension of the bigger model, minus the dimension of the smaller model, the number of ways, the number of directions in which it can go wrong. And if you do a little calculation, it turns out that this is just equal to I minus 1, j minus 1, just by multiplying things out. Okay, so that tells us, so again, the procedure is I calculate the expected, exactly the same as the test in the other situation. The difference, there's two places where it's different. One is that when I calculate the expected counts, I have to use my model. And that's the new piece. I use a new type of model to make this expected count, which is the independence model. And as we go on, we'll see other models we can use. We'll keep using these tests, but we'll change the way we calculate the expected counts to fit these different models that are higher dimensional, which allow for interactions, for example, but restricted kinds of interactions. We're assuming the null hypothesis for all the asymptotics to work and for the chi-squared approximation to work. We have the observed, which is just given to us by our table. We compare them in the sense of, well, we just subtract them or take their ratio, depending on our philosophy here. And then we sum that all up to compute a summary statistic, the chi-squared or the Pearson or the deviance statistic. And then we compare that with the table of the chi-squared with some number of degrees of freedom, where the number of degrees of freedom is just the number of ways I can go wrong, the difference in the number of free parameters from the saturated model that places no restrictions whatsoever, and our model, which does place restrictions.